speaker for this last session is Vernier, from Paris.
Okay. Thanks, Balash, and thanks to the organizers of this really nice workshop. So yeah, I'm gonna revisit six-vertex models, plural. I will explain why I put it in plural, in the light of new and not so new algebraic objects, in particular the Onsager algebra. Well, I explain all of this shortly. And so this is based on a past work with Paul Fenley and his ex-students Ed O'Brien, and also some ongoing work. Okay, so before really moving into what we did, let me just give some quick background on stuff I believe now everybody is familiar with, but just to be. So yeah, six-vertex model, integrability, and quantum groups. Well, six-vertex model, I mean, we've heard it's, we've heard about it in many talks, so I don't need to say much, but so yeah, here we put it on a cylinder. So we have weights depending on configuration at different vertices. And let me recall that weights depend on two parameters, one which is called gamma, the anisotropy parameter, which is typically fixed once for all, and another parameter, u, which is called a spectral parameter, which will be allowed to vary in some sense. So it's quite common to consider the so-called transfer matrix, which encodes the weight of a given row of your lattice. So it's an object, yeah, so it's a matrix which acts on the spin configuration along a given row. And you can write it as a trace over some what we call auxiliary space, which is the horizontal line here, of a product of what we call R matrices. And R matrices are objects which encode the weights at each vertex. So typically they take this form. And so again, they're functions of the anisotropy parameter and spectral parameter. And well, integrability of the six-vertex model can be related to the YangBaxter equation. So I mean, we've heard it like a million times in this conference, but let me recall what it's the form it takes quickly. So it's an equation satisfied by the R matrix relating products of R matrices with different spectral parameters. And from there, it's straightforward to see that you have commutation of transfer matrices for different values of the spectral parameter, but same anisotropy. And from there, a lot follows. So the whole beta on that technology, I mean, many things. A lot of you are experts in. So I won't tell more about this, but let me just briefly mention one aspect, which was also well used in Gilles' talk. So yeah, I said that transfer matrices for different values of spectral parameter commutes. In particular, if you take the logarithmic derivative with respect to spectral parameter around some special points, so here in our conventions u equals to 0, you recover an object which is a sum of nearest neighbor interacting terms, and which takes this form. And this is interpreted as a quantum Hamiltonian. So it's the Hamiltonian of a 1D system, a quantum twin chain, corresponding to the six-vertex model. And did I say the name? So it's called the XXZ Hamiltonian. And so you see that you have the anisotropy parameter, which enters here as a coupling. Okay, so that was the basics. And yeah, now just briefly, quantum groups. So here I'm being very sloppy. So for precise notions, well, we had Bart Vlar's course last week, and also, well, actually last talk by Guillaume, everything was said more, I mean, much precisely. So here it's really sloppy, but basically the idea is that the YangBaxter equation you can view as derived from an underlying algebraic structure, which is a quantum group, which is kind of a deformation of the usual SL2 algebra. So you have representations which are like those of the SL2 algebra, spin 1, half spin 1, and so on. But they're deformed by some parameter q related to the anisotropy by this formula. And so you can think of the YangBaxter equation as well, what I drew in here, namely each line carries a spin 1/2 representation of the quantum group. And so the YangBaxter equation you can trace back to the commutation relations of the quantum group algebra. Okay, well, I mean, there is a lot of really rich algebra behind, but let me just sketch one consequence of this. one consequence is that now you can generalize this equation and you can decide to put other representations here on the line. So for instance, you can decide to put, say, spin 1 representations on each line. And from there, you're going to get another integrable vertex model. And we call that the higher spin six-vertex models. And alternatively, there's another way to obtain these, which is called the fusion procedure. And also in last talk by Guillaume, we had a summary of this. So you can put any half integer spin representation. And so just to give you an example, if you put spin 1 representations instead of spin 1/2, what you're going to get instead of the six-vertex model is a 19-vertex model originally found by Zamochikov in FATF in 1980. And to finish with this, just a bit of nomenclature. So these higher spin six-vertex models, the corresponding Hamiltonians I will sometimes call higher spin XXZ, but they're not literally the XXZ Hamiltonian where you replace the sigma operators by higher spin generators. They have a more complicated form, but they are usually what we refer to as integrable XXZ, higher spin XXZ Hamiltonians. Okay, so that was a quick summary, and now let me move to really what I want to talk about. And the aim of this talk would be to revisit some aspects of these models, or in particular, the higher spin six-vertex models at some special, what we call root of unity points. And we want to revisit them, showing the appearance of finer structures that what you could get from the quantum group. So the idea is we want to, go beyond the quantum group description. And so there will be two parts. So the first part on Onsager symmetries, we'll pretty much review what we did with Ed and Paul. And then in the second part, this is more work in progress, but really related to the first part. Okay, so Onsager symmetries in a root of unity six-vertex model. So I should say a few words about what I mean by Onsager symmetries or Onsager algebras. I mean, we have experts in the room, Pascal in particular, and also in last talk by Guillaume, Q Onsager was mentioned, but let me just give some really quick recap. So this also goes back to the original solution of the Ising model by Onsager in 44. So I borrowed this figure here actually from Onsager's paper. So the idea again is to put the Ising model on a cylinder. So here you have a lattice, you have spins lying on the vertices, so they take plus or minus values. And again, you want to consider the transfer matrix, which generates the weights of this model. And so the transfer matrix is an object which acts on vectors here, which encode the spin configuration in a given row. And the transfer matrix you can write so this is all Onsager's work. You can write as the product of two terms, here highlighted in blue and orange respectively. And these two terms, V1 and V0, they encode the couplings on the horizontal rows and vertical rows respectively. And it's actually convenient to write these transfer matrices in terms of some local matrices which act on these vectors here. And these matrices, we call them taus and sigmas, acting on each side. And they act quite simply. You see that tau on site J just flips the local spin, while sigma measures its value. I mean, that's one representation of it, but you can also move to different bases where basically they're swapped. And well, independently of the basis, you can just remember the algebra satisfied by these matrices. On different sides, of course, they commute. They all square to 1. And importantly, tau and sigma anti-commute on different sides. And the last important notion is that, well, you probably know that in Ising model, there is some Kramers-Wannier duality between high and low temperature. And well, it's naturally implemented in terms of these matrices through the following mapping. So tau on one side gets mapped to the product of sigma and sigma on two neighboring sides, which itself becomes mapped to tau, but on the next side again. So that's how duality acts, because mu is plus and minus 1. Okay, so let's introduce two objects called A1 and A0, which are the arguments of these exponentials here. So you see that, well, they're dual to each other, and they're the Kramers-Wannier duality. And those two guys are really the instrumental bits in Onsager's solution. And I won't go into detail, but what's interesting for us is the following. they generate some algebra. So if you take commutators of them and commute and commute and commute, you'll see that you generate an algebra which you can express in terms of two infinite set of generators, a_m's and g_m's for m positive or negative integers, which satisfy this algebra here. And this is, well, the celebrated Onsager algebra. And this is, I mean, from there and a few more details, Onsager was able to solve the Ising model, basically. So that's really instrumental. And after Onsager's paper, a bit more, I mean, some really important progress, further progress was made by two works, first by Dolan and Grady, and then another one by Davis, where they showed that it's actually enough to generate the Onsager algebra to prove that A1 and A0 satisfy two identities, which actually are related by duality here, and which take this form. So they're identities relating the commutators of A1s and A0s, and they are called the Dolan-Grady relations. So if you can have, I mean, if you can exhibit two operators which satisfy these equations, then it's granted that they are going to generate an Onsager algebra. And that's actually quite powerful. Okay, so that's this, well, I mean, basic summary of like basic facts about the Onsager algebra. And now let me proceed further to what I want to show to you. And so the first step is to introduce what we call clock models, which are a generalization of Ising model, but to end state spin. And this is quite, I mean, we did not invent that. That's quite standard. Like a lot of authors use them for different reasons, Baxter and so on. Well, it's easy to see that, well, the correct way to generalize the algebra of taus and sigma matrices to end state spins is to introduce those matrices here. So now we have sigma, sigma dagger, and tau dagger, but they're related to these equations here. Again, they commute on different sides, and they don't anti-commute anymore. It's a bit more complicated. There you have this relation here, which involves some nth root of unity. But so that's the algebra. Again, we don't need to think of a particular representation. I mean, most of what we do just relies on this algebra, but it's quite convenient to always have a representation in mind. And in practice, we'll deal with the tau basis representation, which is the representation where tau is diagonal. And so tau typically takes this form on a given site, while sigma is just, a clock shift of the spin modulo 1. So that's a convenient representation. And again, for these matrices, you have a Kramers-Wannier duality, which acts as follows. So it's generalization of what you have for the n equals 2 case. Now, tau gets mapped to sigma dagger sigma, which itself gets mapped onto tau on the next site. And well, these have been used a lot. There are many relevant Hamiltonians, which you can find around the literature. They're also related to parafermions. I won't say much, but just to give you a flavor of what a typical Hamiltonian looks like, well, if you want nearest neighbor interaction, well, it's going to be the sum of terms here, which are different powers of sigmas or sigmas or taus with different coefficients. We call them clock Hamiltonian because they have a clock symmetry or Zn symmetry. Namely, if you multiply all sigmas by omega, you can see that the Hamiltonian remains invariant. So that's the basic symmetry of the models. And you can have more symmetries. So for instance, if you impose all the alpha hats coefficients to be equal to the alpha's coefficients, then you have self-duality, which will be useful for us. Another special case is that if you take all alphas to be equal to something and all alpha hats to be equal to something, then you promote the Zn symmetry to Sn symmetry, and now what you recover is the Potts quantum Hamiltonian, and you have other cases like the Carr-Potts model and so on. So that's pretty standard material. And now let me move really to what we did. And this starts from the following observation. So, well, sorry, go back to this thing here. So we have linear combinations of taus and sigmas with some coefficients. If you choose the coefficients in some way, so let's choose alpha A equals to this thing here. What we see is that the local sum of tau matrices takes this form in the tau basis. So I don't know if it's big enough for you, but if you see well enough, you can see that this is just the equivalent of the longitudinal magnetization Sz for a spin n-1/2 representation. So it has eigenvalue which jump by 1. And so if you now take the sum of these guys on the whole lattice, what you get is a U1 charge, or something you could interpret as a particle number. You know, it has integer eigenvalues. And so the natural question from there is, okay, so we had Hamiltonians which we could build which have like Zn or Sn symmetry, but could we promote them to having U1 symmetry, namely conserve the number of particles? And well, it might seem a bit strange to ask this question, but you'll see a lot follows from there. So yeah, the question is, can we modify? Yeah.
So is generally Hamiltonian is Hermitian or not?
Oh yeah, I didn't put the constraints. I want hermiticity. In my case, I mean, in this generic case, you need another constraint on the alphas to have hermiticity. You need something like alpha of n minus a equals to alpha a star, something like this.
The second question is, I mean, when I have the complete representation of matrices in mind, then it would seem to me that the particle numbers are somehow conserved because sigma here and sigma there.
No, that's the thing, because sigma dagger sigma is not s plus s minus. Sigma dagger sigma can well, better right.
One shifts clockwise, the other shifts anti-clockwise.
Yeah, but then okay, precisely, one shifts clockwise and one shifts anti-clockwise. But clockwise can mean go from n to n plus 1, but it can also mean go to from big N to 1. And so it means that this guy here either preserves the magnetization or changes it by n. So you only have, okay, another way to say it is that this conserves magnetization only modulo n originally. Other questions? So yeah, so we want to promote this, well, symmetry modulo n to an actual conservation law. And we want to do it remaining nearest neighbor, because I mean, we want to keep things simple. And also we want a self-dual Hamiltonian, and the motivation for this will become clear in the next slide. So can we achieve that? And the answer is yes. So, well, the formula looks a bit ugly, but well, that's how it is. We can construct for any n this Hamiltonian here, which I mean is not obvious from the formula, but you can check preserves the Q charge, is self-dual. This you can see because for every term you have the dual here with the same coefficients, and it's also Hermitian, and it's also nearest neighboring parents. So we have these Hamiltonians here, which we call the U1 invariant clock models. Okay, so yeah, I presented something which might seem a bit strange and ad hoc, but now you see that a lot follows from there, and a connection with six-vertex model will become clear shortly. So let me recap what we have. We have a set of Hamiltonians, Hn, which are self-dual and commute with Q. So Hn commutator with Q equals to 0. And this equality only follows from the algebra satisfied by the sigma and tau matrices. So if you take the dual of this, then the equality should still follow. Hn is self-dual, so it doesn't change, but Q is changed. And Q becomes its dual, Q hat, which, well, simple expression follows. And the important thing is that in turn, Q and Q hat do not commute. So Q hat is going to be the sum of sigma dagger sigma terms. And yeah, as I answered to Balash, you see that it's actually the sum of 3 terms. One term, Q hat not, which does commute with Q, but 2 terms, Q hat plus and minus, which don't commute with Q, and instead change it by plus or minus n. Okay, so recap, Hn commutes with Q and Q hat, which in turn don't commute with one another. So they generate some kind of non-abelian algebra, which is a symmetry algebra of H. And so the question is, what is this algebra? And well, to find out what is this algebra, let's play a bit with commutators. So Q hat is the sum of these guys. If we commute with Q, we're going to kill Q naughts, and Q plus and minus are going to be multiplied respectively by plus and minus n. So we get this. We commute again, we get this. We commute again, we get this. And now if you compare this and this, you get this equation here, and you take the dual, you get this equation here. And these 2 equations, they're nothing but the Dolan-Grady relations for, well, I mean, after having renormalized Q and Q hats. So A naught and A1 are proportional to Q and Q hat respectively. So this means that just from these 2 simple observations, we have granted that Hn commutes with the whole Onsager algebra. And well, this is actually quite powerful. There are many, many interesting consequences, which, well, we explored in this paper, and I won't give details here because that's not the main point, but basically, I mean, there are, yeah, many interesting physical consequences, in particular on the Bethe-Ansatz solution of these models. But yeah, here, instead, what we want to focus on is more the relation of all I'm saying here with the six-vertex model, which for the moment I guess is quite obscure. And yeah, as I was advertising, underlying algebraic structures. Okay, so yeah, what's the relation with the six-vertex model? So yeah, I told you HN commutes with Q, but as we just discussed with Balázs, it's not obvious from its explicit form. So we can actually bring it back to a manifestly Q commuting form. And so for this, we replace the sigma dagger sigma terms by, I mean, we re-express them in terms, instead of sigmas and sigma daggers, some new operators, S plus and S minus, which you can write in terms of sigma and sigma daggers, but for clarity, let's write what they are in the tau basis, and they're just spin raising and spin lowering operators. And from there, the Hamiltonian takes this form, and here now you see it clearly commutes with the charge. Okay, fine. Small technical step, we have to make a small change, local change of basis of on this Hamiltonian, so we will just remove these factors. It's not really important, but okay, I'm just putting an approximately equal sign here because you might have some boundary twist terms, but you can also remove them if you take L multiple of n, so you don't really need to care about them. So let's just keep in mind that H is morally this thing. And now, well, relation with the six-vertex model, well, there we go. Let's look at the first few values of n. Well, n equals 2. H2 is nothing but the so-called XX spin chain. So it's a special case of the XXZ model at Q equals to EI pi over 2. N equals 3. Similarly, H3 is the, between quotes, spin 1 integrable XXZ model related to the Fatiev-Zamolodchikov 19-vertex model I told you about before. Again, at some special root of unity value of Q. And more generally, we claim, so it's not rigorously proven, but there are a lot of converging indices that Hn for generic n is some higher spin integrable XXZ Hamiltonian, again, at some specific root of unity value of Q. Okay. So yeah, summary, Hn, which we showed commuted with the Onsager algebra, is related to higher spin six-vertex models, which, as I told before, can be constructed and interpreted with quantum groups and everything. So in principle, well, we could recover this whole Onsager structure and so on from the quantum group. And indeed, many features which I described can be recovered in this fashion. So for instance, Hn and for, I mean, other conserved charges can be constructed from a transfer matrix, which is based on, well, spin n minus 1 over, I mean, so higher spin reps, so half integer or integer reps, which graphically I picture as follows. Okay, but also the Onsager algebra and so more complicated commuting charges, you can build in terms of transfer matrices. And this is something I didn't tell before when I was introducing quantum groups. For root of unity parameters, you have more complicated representations which have no correspondence in SL2, so they're not integer or half integer representations, so they're called complex spin representations or cyclic representations or semi-cyclic representations. You have different types of them, and we can use at root of unity these representations to build transfer matrices, which again which will commute with Hn, and we can show that these indeed generate the Onsager algebra. So it's all kind of consistent. So that's what we studied in this paper, and there were also some further study and generalization by Yuan Miao recently, and I believe he's going to talk about some of this in his talk on Friday. Okay, so well, we might stop there, but my point is that actually there are some aspects, and I think some really important aspects, which kind of escape the vertex model quantum group pictures. And I can go into, I mean, I cannot go really into the details, but when you do calculations, you find that there are a lot of relations which you see in terms of Onsager algebra, which are not natural in the vertex model. And to give you a simple example, well, yeah, a blatant example is duality. Duality was clear in the clock model. I mean, we knew how to map tau to sigma sigma, and it had a clear meaning, and it was clear that Hn commutes with duality. Now we wrote Hn in terms of a vertex model. Now, what does duality mean in this setup? It's really not clear at all. And what does, I mean, how do you see from the vertex model or from the six-vertex model that H is self-dual? That's not clear at all from this picture, at least I believe. And so that is what motivates my second part, which I call beyond the quantum group in some sense. And well, so that was mostly motivated by the questions I just asked, but actually I got a lot of inspiration from a very nice recent paper. Some of you might have noticed, which came out on the archive last spring by Bajanov and Sergeyev, and which is called an Ising-type formulation of the six-vertex model. So I'll just review briefly what this paper does. I mean, some of it, because it has more aspects. I didn't really explore everything. It's really rich. So what these guys do is they start from a lattice, which really has the structure of an Ising lattice. Namely, you have degrees of freedom, which live on vertices, and they interact pairwise with some interaction strength. So this is why they call this Ising-type formulation. It's like a spin model, or Ising model. Except that now, instead of being just +1 or -1, the spins, I mean, can take any integer value. Okay. And so what these authors do is that they choose interactions between spins such that they obey the celebrated star triangle equation, which graphically takes this form. I don't have time to, I mean, for those who are not familiar with star triangle, to tell a lot about how it works. But since there was an introduction about YangBaxter, it's actually quite helpful to think about this equation in terms of YangBaxter equations. And the idea is that behind this construction, you can think of lines here in dashed, which carry spectral parameters. So the dashed lines. And so whenever these lines cross, you have an interaction, which is parameterized by the incoming spectral parameters. And in this formulation, the star triangle equation, you can just view as the YangBaxter equation. So they're kind of two formulations of something of the same thing. Okay, so Bajanov and Sergeyev parameterize the interactions such that they satisfy the YangBaxter equation, the star triangle equation. And from there, they construct a vertex model. And the way they construct a vertex model is the following. So they have, is it better? And also to test the camera, which moves. So their building blocks is this thing here. And what they define as, and this gets mapped to a vertex model, which, well, whose R matrix is written here. And so you move from these face degrees of freedom, or these spins, to vertex degrees of freedom, which live on the edge here. And these degrees of freedom are defined as the difference between adjacent spins. Okay, so again, they take unrestricted integer values. But so, well, you can show different things. Well, you can show quite straightforwardly that these vertex models satisfy the YangBaxter equation, and this is just a consequence of multiple application of the star triangle equation, star triangle relation. And what's important for us, and well, what's actually the whole point of this paper is that, so you see that a vertex model, typically we think of two lines crossing, which each carry a spectral parameter. Here, it's a bit more rich. You have two lines on each side which carry, so you have 4 spectral parameters. But what these guys show is that if you now constrain the spectral parameters, so impose some relation between U and U prime incoming here and V prime incoming here, then you're able to truncate the R matrix. So you're able to truncate these indices into living in some finite sets. And what you recover is the R matrix of UQSL2, so some higher spin XXZ R matrix, higher spin 6-vertex R matrix, interpolating between two integer or half integer spin representations. Okay, so that's actually pretty brilliant, because the message is that behind these higher spin XXZ models, you have actually some hidden structure where with twice more lines with twice more spectral parameters, and the YangBaxter equation is just, follows from a multiple application of the star triangle equations. Okay, so that.
Sorry. So then you have 4 crossings, and so how does this work a little bit more in detail? So on the right hand side there is a vertex which takes, for example, difference a minus c. This I see, but then so I don't see how to put it together with 4 crossings there. So what is the correspondence? Fix some integers or half integer s1 and s2. Okay, these are the representations that you want to take. Imagine that, okay, I want to take the R matrix intertwining between, say, spin 1 and spin 1 representation. So let me take s1, s2 equals to 1. Okay, so that fixes some relation between U prime and U, V prime and V.
So now I have just two parameters, u and v, two free parameters. And the R matrix, which you can truncate from there, is just the R matrix R of u minus v, of which intertwines between the two usual spin ones.
Summation of the middle index.
Yeah, oh yeah, sorry. After summation of the middle index. Yeah.
Then you sum over an infinite number of.
Yeah, but the nice thing is that it truncates. It can be truncated.
So for some of the spin weights are non-zero only for finite values.
Yeah. Oh yeah, some. Since I don't have much time, I was a bit sloppy, but there is. I actually wrote it. There is just one constraint. They're unrestricted, but you have some ordering constraint, and you can only increase when you go up or something like this. So that gives you a bit more constraint, and from there, that's where you get a finite summation. Okay, so that's basically what they did, and so let's see what we can do from there. So let me recap what the situation for the Bazhanov-Sergeyev paper. That's what they do is for generic Q, or generic anisotropy. So I recall that the heights of the spins take unrestricted values, and only once you specify two representations, say S1, S2, then you fix constraints upon the spectral parameters, U prime, VV prime. So what you get, instead of 4 free parameters, you get just 2 parameters. And then, the R matrix is of different forms, so you just get a 1 parameter dependent R matrix, R of U minus V, as I just said. And that's consistent with the picture we have from quantum group, where we know that there is just a 1 parameter family of R matrices. But now the idea from there is that, that's where Bazhanov and Sergeyev ends, and that's where we want to start. For Q, or root of unity, we know that there are way more general families of R matrices, which are inherited from this exotic representation. So in principle, we have more free parameters. And so the question we want to ask is there a way that we could do something similar, but instead of imposing some constraint here and getting some truncating in the first place, and then having an R matrix with all those parameters free and recovering all the complicated structure from the quantum group in this exact same way. And this is what I want to do from there. And for this, let me just go back to, the solution of star triangle equation for end-state clock models, namely how much time do I have? Just
10 minutes, including questions.
Oh, great. Okay. Same star triangle equation as before, but now the heights do not take unrestricted values anymore. They are considered modulo n, so they take n possible values. And so we want to look for solutions of these. Well, actually, we don't look for them. I mean, they're in the literature. I mean, they're well known, and in particular, there is this very seminal paper of Baxter, Perk, and Aoyang, where they wrote the generic solution of the star triangle equation. I mean, it takes a really complicated form. I won't go into the details, but let me just mention a few aspects. So first, you have two types of weights depending on the orientation of the arrows meeting. So you have weights which we call W and weights which we call W bar. Okay, they're not simply parameterized by two complex number as we were used to before with spectral parameters. Now they're parameterized by different parameters A, B, C, D, which are related to some constraints, and so overall they live on some complicated genus surface. So it's a really complicated solution. But you have some cases in which the solution simplifies, and in particular, it's the case for the so-called Fatiev-Zamolodchikov solution. And Fatiev-Zamolodchikov, same authors, but different paper from the Zamolodchikov-Fatiev spin one chain I mentioned before. Other solution where if you take a specific case of these A, B, C, D variables, you can see that the weights now recover some usual good old difference properties in terms of two incoming spectral parameters. Okay, and I'm just mentioning this because we're going to use this solution, but you don't need to, I mean, it's not so important actually. And let me just mention another aspect of this solution is that in the particular case where the two sets of rapidities here, or the two spectral parameters are equivalent, then the weights simplify a great deal. So the W weights become 1 for any values of the spins, any values of the I and K spins here. I hope this is big enough for everyone. And the W bar W bar weights instead become Kronecker delta. So they impose those two spins here to be the same. And this, geometrically, you can really interpret as you would do usually for a vertex model. Maybe, in vertex model, you have a special point where the R matrix is the identity. Well, here's the exact same thing. So instead of crossing, the two lines just avoid each other, and that gives a perfect interpretation for these ways. Okay, so that's the setup, and now let's try and construct a vertex model from there. And there are actually two geometries to do so. And they're pretty much equivalent. So we'll discuss, we won't need to really deal with the two of them, but let me just sketch what they are. So the first geometry is the so-called star geometry, and it's exactly what Bajanov and Sergeev had. So the building block, the R matrix of the vertex model is this thing here. And the vertex degrees of freedom are the difference between adjacent heights, so as before. But now, since the heights live in Zn, the vertex degrees of freedom live in Zn as well. Other geometry, which is called the diamond geometry, now the building block is this, and the vertex degrees of freedom are the spin degrees of freedom themselves, which are again in Zn. And it's slightly simpler in the sense that you don't have to sum on some inside spin, but morally it's really equivalent, and the two are related to some kind of Fourier transform. So they're equivalent. And in practice, I'll be dealing with the second one because it's a bit simpler. But if you prefer the first one, you can use the first one. And so the claim I want to make here is that from this geometry and these solutions of Zn here, we can recover the root of unity six-vertex model. So in the Onsager language, Hn. We can also recover the complicated exotic quantum group representations. So in the Onsager language, the Onsager symmetry. And the big novelty compared to the vertex model or quantum group language is that we can make perfect sense of Q, Q hat, and duality. And that might sound like a detail, but for me, it's important. And it seems important. And also, since you have this factorization, I think it's really relevant. Okay, so let me show you a bit more in detail how this works. So yeah, I was telling you about the two geometries. I stick to geometry 2 here. So I have an R matrix of the vertex model, which takes this form. So remember, the vertex degrees of freedom are just the spin themselves. Originally, we have 4 parameters, U prime, VV prime. Let's temporarily specify these parameters. Actually, let's specify to the solution of Fatiev-Zamolchikov. In principle, I could take any solution of Baxter, Perk, or Young, but let me specify to Fatiev-Zamolchikov. And let me specify the spectral parameters to take this value here. So I have one free parameter, which I call V. And what I get, so is a 1-parameter R matrix, R of V, which I claim is exactly this R matrix of the spin n-1/2 six-vertex model at root of unity. So that's exactly what we want. Okay, well, that's a good start. So from there, we can build a family of commuting transfer matrices. So we have some vertical spectral parameters, some horizontal spectral parameters. These are fixed, and these, well, they have some free parameter V, and so transfer matrices for different values of V, they commute. And we recover from there exactly what I showed you before, the integer or half integers spin transfer matrices, which you can build from the quantum group. And in particular, if you take the first log derivative with respect to the spectral parameter, then you recover Hn. Okay, but then my whole point, if we want to make some progress compared to the Bajanov-Sergeev paper, is that now we didn't impose some constraint on the spectral parameters. So we can, for instance, here choose to take another value of the spectral parameter and we still get commuting objects. So let's do that. Let's put here instead of V some W. And what I recover precisely is some cyclic representation of, some transfer matrix built on a cyclic representation of the quantum group, which is specific to root of unity. And well, this is precisely what generates the Onsager symmetry and so on. And just to give you a flavor of what it is at the Hamiltonian level, if you take the log derivative now of this object here, what you get is this thing here, which now is not self-dual anymore, it's all under duality. I don't have a big physical interpretation for this, but yeah, that's what it is. Okay, next thing I was advertising is that Q, Q hat, and duality make perfect sense in this formulation. Well, I'll just sketch this without details. Let me just warn you that Yeah, I'm done almost. That you need to go beyond the Fatih-Zamochikov solution. You need to go back to more complicated solution of this, but you can do this. And from there, you can construct Q, or rather the generating function of Q, as a transfer matrix with the exact same geometry, same for Q hat. And duality is really natural in this framework. It just amounts to a translation by half a site. So it really makes perfect sense. And yeah, so that's pretty much where I stand. It's some ongoing work, so I have some missing parts. In particular, I told you that we can recover the whole set of complex, of exotic quantum group representations. I do have some problems with complex spin representations, which I couldn't not generate yet from this framework, but I believe it's just, I'd be surprised if it could not be dealt with. And yeah, I'll skip that, but there is a small technical issue, aesthetical issue rather, which is that commutation with Q, it's shown in this framework rather indirectly, and I'd like a more direct proof. But well, yeah, let's skip this. And yeah, conclusions. Yeah, we could really. I like this sentence in Bajanov and Sergeyev's paper, so say it out loud. So yeah, the possibility of the Ising-type formulation of these models, these vertex models, raises questions about the precedence of the traditional quantum group description of the vertex model. Indeed, the role of a primary integrability condition is now played by the star triangle equation, which is not natural in the standard quantum group setting, but implies the vertex-type YangBaxter equation and commutativity of transfer matrices as simple corollaries. And so here what we've done is we addressed the counterpart of this specifically at root of unity, where you have some richer structures which appear, and in particular, yeah, linked to exotic quantum group representations, and which, as I knew from this paper we had previously with Paul and Ed, that they have close connection with Onsager algebra. So yeah, there are, different perspectives. This is not an exhaustive list, but yeah, I want to really fully understand these complex spin representations and see how we can recover some usual features of beta ansatz or transfer matrices from there, like TQ relations, beta ansatz, and so on. And yeah, I want to investigate other aspects like relation with free fermionic vertex, free fermionic models like Paul Finley deals with. Yeah, that's all. Thank you. Sorry if I'm a bit late.
Thank you for a nice talk. Any questions from the audience?
So, at the beginning, you mentioned that the key ingredient in this story of this university is to play with this kind of Vernier duality.
Yeah.
So, you know that for the Onsager algebra, you have this embedding in algebra +2.
Yeah.
Do you understand how this kind of Vernier duality?
No. And I'm not saying it can be understood, but personally, I don't know well enough about the loop algebra. But
yes, I think you mentioned actually that it was not clear.
What do I mention?
I think at some point you mentioned that it's in the setting of the quantum in terms of the express exponents, but it was not clear how this kind of variability.
Oh yeah.
Disconnected.
Oh yeah. Probably. If the loop algebra makes sense originally in the vertex model, yeah, the whole point then is to translate these things which are natural in the clock model, like duality and so on, in the vertex model language. So Onsager algebra, fortunately, it's natural in the vertex model because you're used to it, but we know also it's natural in the clock model because we know how to express it there. The loop algebra, I don't know if it makes a natural sense in the clock model formulation. So, I don't know if that's your question, but if so, I don't know the answer. But yeah, sure.
Other questions here or online?
I think you.
Sorry, the Hamiltonian. So there's the one which commutes the QS.
Yeah, this one.
Is it so for n equal to the x function? So
yeah.
It's critical?
Yeah.
Do you know for general n?
Yeah. Because they're just they're always at Q root of unity, so they're always gapless, and we know that the higher spin XXZ models, they're always gapless, and I don't remember the authors, but the associated CFTs are known, so there's some kind of paraharmonic CFT. It's written somewhere in our paper with Paul and Ed, but Yeah.
The Q has generated the real Onsager. It's not the Q form Onsager.
Yeah.
So the Q appears in the representation of the original Onsager.
Yeah.
Did I understand then that in your construction for the x-axis chain, for instance, you have two charges which look like the mathematician charge. So what are they?
Well, I mean, you have two charges originally, but then if you take commutators and commutators, you get many of them. So XX Hamiltonian is just, you can write it as sum of sigma plus sigma minus sigma I plus 1. I think if you take something like Q plus equals to sum of minus 1 to the power I sigma I plus sigma I plus 1 plus, this is, for instance, one of those charges. And you take the Hermitian conjugate of this is another charge. And actually, I think, well, Q hat is something like sigma. Yeah, no, I'm going to get it wrong. But basically, I mean, you have Q plus, which that's Q hat plus. Q hat minus is the conjugate of this. And Q hat naught is this with a minus. So Q hat is the sum of all these.
This Q plus and this
Sorry?
This one, if you put it to high enough power to be 0.
No, well, no, if you locally takes this to be 0, I mean, if you take locally the power of this, of course, it's going to be 0, but you can take sigma I plus 1 times sigma j plus 1.
Yes, but if you put the small part to the power n, or n is the sum.
Oh, to the power n.
I thought this was like the magnetization.
Yeah, no, okay, but it's not Hermitian, so it's yeah, so it's going to be like tri-diagonal or something like this.
Yeah, I think we should continue later the
Okay.
discussion. So thank you.
Thanks.
Thank you.